When you want to study sequential circuits, the first thing you need to know about is the most elementary sequential element, sequential device, and that for us will be the JK flip-flop. This is not historically the simplest flip-flop to be discovered, but this has all the nice properties that we would like to have, and so we will not study, for example, the so-called SR flip-flop. We will work only with the JK flip-flop as the starting point and as the fundamental element for all our studies of sequential circuits. So what is the JK flip-flop? Here is a black box representation of the JK flip-flop. We are not going to discuss what lies inside. Essentially, it's an interconnection of gates. And what we will only look at is the behavioral aspect. What does this JK flip-flop really do? That's our concern. Now, let us look at all the various leads coming out of this JK flip-flop. On the input side, which is the left side, you have J and K. And on the output side, we have Q and Q bar. Now Q is called the output and Q bar is called the complementary output. It is nothing but the complement of Q. If Q is 1, Q bar is 0. If Q is 0, Q bar is 1. Therefore, it comes down to asking how J and K determine the value of Q. For this, we have to understand one more thing, that if you change J and K at a particular point of time, give them new values, the result of the change at the input is not immediately manifested at the output, but after the next edge of the so-called clock. Now let me explain what that means. We have always a certain terminal called a clock terminal in the context of a JK flip-flop. In this case, we have what is called an edge-triggered, positive edge-triggered clock terminal. And this sharp cone that we have drawn over here essentially represents that it is a positive edge-triggered flip-flop. A negative edge-triggered flip-flop would additionally have had a little circle like this. But since it is positive edge-triggered, the one in the lab handout, we need to discuss only what the positive edge-triggered flip-flop does. Now, time is divided into two parts in the case of the behavior of a flip-flop. The first part is the before and the latter part is called the after. The output manifests itself in the after period as a result of and dependent upon the changes, the values of the input just before the transition occurred. In short, let us say that we have this dividing line. This dividing line on the time axis is essentially determined by where a positive transition, that is a 0 to 1 transition, occurs on this, the signal applied to this terminal. So this, let us say, is the clock. Here we have the positive edge of the clock occurring at the boundary between before and after. Now let us say that before this edge, J and K are 0 and 1. Let's say this is J and this is K, and let's say J was 0 and K was 1. So what is this going to do? This is going to ensure that though nothing happens to Q as soon as J and K assume these values, on the first opportunity after a positive clock edge is applied to the clock terminal, the output Q will be forced to 0. That is, if Q were equal to 1, if Qn determines the before value, before edge, and Qn plus 1 is the after edge value, then it says that irrespective of Qn, that is to say whether 0 or 1, Qn plus 1 will be 0 when Jn, Kn are equal to 0, 1. That is, when Jn is 0 and Kn is 1, irrespective of what value the input had and the output had, the input and the output had before n equal to 0, before the edge. After the edge, it will always have Q equal to 0. This is called the reset operation. Likewise, if Jn equals 1 and Kn equals 0, we have the set operation. That enforces that Q n plus 1 equals 1 irrespective of Qn. In short, these synchronous set and reset operations, they are called synchronous because their effect manifests itself only after the clock edge occurs, the positive clock edge occurs, not at the time the input changes, but at the first opportunity of a clock edge after the input has been applied. These set and reset operations force Q respectively to 1 or to 0 irrespective of the previous state of the output. But there are two other things you can do to J and K. After all, J is a bit and K is a bit. So while we can have Jn, Kn equal to 1, 0 for setting and 0, 1 for resetting, we also could consider what happens when Jn and Kn are both 0 or both 1. And these are the next two behavioral aspects of the JK flip-flop that we will discuss. So if Jn and Kn are both equal to 0, then the output Qn plus 1, output subsequent to the next clock edge, remains unchanged. That is to say, Qn plus 1 equals Qn. So now you see, this is a case where Qn plus 1 is determined by what its previous value was. If its previous value was 0, it is still 0 at Qn plus 1. And if Qn was 1, then Qn plus 1 remains 1. Unlike these two cases where it was forced to particular values, here it is just maintained at the previous value. The last option is to keep both J and Kn equal to 1. And this forces a reversal of the output state. That is to say, Qn plus 1 equals Q. Qn bar complement. That is to say, if Qn were 0, it will be forced to 1 at n plus 1, and if Q were 1, Qn were 1, then Qn plus 1 will be forced to be 0. So these are the two instances of dependent operations. These operations either preserve when j and k are 0 the previous values, or reverse the previous value as it happens when j and k are both equal to 1. So all this is summarized in this so-called truth table of the JK flip-flop. The JK flip-flop truth table says if Jn and Kn are 0, then Qn plus 1 is the same as Qn, that is, it remains unchanged. If J is 0 and K is 1, if J is 0 and K is 1, then as I said, we have a forced reset. So Qn plus 1 becomes 0, irrespective of Qn. It's not a function of Qn. If J is 1 and K is 0, then you have a forced set. It is set to 1, irrespective of Qn. Finally, when both J and K are 1, Jn and Kn are 1, then Qn plus 1 becomes the complement of Qn. This is called the truth table. It represents what the flip-flop will do on specific inputs at the next clock edge, subsequent to the next clock edge. So please understand the significance of these subscripts over here. Jn and Kn represent input values, Qn represents the output value before the clock edge. Qn plus 1 represents the new output subsequent to the clock edge as determined by the values of Jn and Kn. So the inputs are changed before this point. The output is affected after this point. That's the fundamental important part to understand about flip-flops. The next thing we talk about is called the excitation table. The truth table tells you how it behaves, but it is not the most convenient thing to have when you're designing something. When you're designing something, it's not a question of what it does, so much as asking what you need to do to make it behave in a certain manner. And what the excitation table gives you is precisely this. It tells you what inputs to apply or what inputs you need to apply in order to enforce certain kinds of output transition behaviors. For example, if Qn plus 1 is the same as Qn, or rather if Qn plus 1 is 0 and Qn were also 0, you can characterize it in two ways. You can say the output did not change, A, or you can say the output was made to be 0 irrespective of the previous state. Now if the output is made to be 0 irrespective of the previous state, then it was a reset operation. In short, Jn and Kn should have been 0 and 1. But you could also say the output just remained what it was. And in that case, you would say that 0, 0 applied to the input would also have achieved the same end. In short, to get a transition from Qn equal to 0 to Qn plus 1 equal to 0, you either need to apply 0, 0 as J and K, Jn and Kn, or you can apply 0, 1. So 0, 0 and 0, 1 so if Qn plus 1 equals Qn equal to 0, this can be looked upon as either a reset operation where you would say Jn, Kn are 0 and 1, or you could look at it as a maintain operation, which is obtained by saying Jn and Kn are equal to 0 and 0. In short, Jn has to be 0. Kn can be either 1 or 0. That is, Kn can be anything. This means that the J and Kn entries in the excitation table against Qn plus 1 equal to Qn equal to 0 would be 0 for Jn, because it has to be 0 in either case, and x for Qn plus 1 for Kn. In the same way, we can look at the other possibilities. Suppose you have a case where Qn equals 0, Qn plus 1 equals 1. This change can either be interpreted as a set operation, which is obtained by Jn Kn equals 1, 0, that is setting the flip-flop, or it could be also obtained by a flip operation. A flip operation is an operation that reverses the existing value being 0 and the new value being 1. So you could also get this by saying Jn and Kn are 1 and 1. Either of these inputs will make Qn plus 1 equal to 1 when Qn was 0. In short, you need to make sure that Jn is invariably 1, but Kn can be anything. That's 1x. Third, when Qn equals 1 and Qn plus 1 equals 0. Here again, you could say that Jn Kn either are carrying out a reset operation, a forcible making of 0 of the output, which is obtained by 0, 1, Jn equal to 0, Kn equal to 1, or a reversal, a flip, and that is equal to 1 and 1. Both these choices of the inputs will make Qn plus 1 equal to 0 when Qn was 1. In short, this amounts to saying that Kn has invariably got to be equal to 1, whichever way you interpret it, but Jn can be anything, can be 0 or 1. So you get x1. It is for x1 of Jn and Kn that you get the 1 to 0 transition of the flip-flop output. Finally, if you want to have output 1 when the previous output were also 1, then you have the last case. You have Qn equals Qn plus 1 equals 1. Again, this can be looked upon either as a maintain operation, by which I mean Jn Kn are equal to 0, 0, that is, make no change, or it could be looked upon as a set operation, because that would, irrespective of Qn, make Qn plus 1 equal to 1. So what is a set operation? A set operation would be 1, 0. Jn equal to 1, Kn equal to 0. So either of these two pairs would give us the transition we want in this case. And this gets summarized as anything for Jn and 0 for Kn. x0. This is the excitation table. And with all these things explained, we have nearly come to the end of the important, relevant part of the JK flip-flop behavior. There are a few exotic points that we have still left out. What is SD and what is CD? SD and CD are called the master reset and master set terminals, and we are never going to use them, so we are not going to talk about them. So now that we know what a simple single JK flip-flop does under various kinds of input conditions, let us consider one of the most common applications of a JK flip-flop to do what is called clock division. What we mean by this is the following. Let's say we have an input clock signal which is of a certain frequency, let's say 1 kilohertz. So I will make a few pulses of that clock and apply those pulses to the clock input of the first of these two flip-flops, after ensuring that both J1 and K1 have been kept at 1. We know that when J1 and K1 are both kept at 1, this flip-flop will work in flipping mode. That is, that every time it encounters a positive edge of the input clock, it will flip its current state to the opposite state. So let's see what happens. The clock first. So when this input clock is applied at the clock input of the first flip-flop, we know what it does. Let us assume that to begin with, the first flip-flop was in some state, let's say the 0 state. And since it was initially in the 0 state, Q1 at the first positive clock edge that it encounters will flip its current state and go to the 1 state here. Now, having done this, it will remain in that state until it encounters the next positive clock edge. This is the next clock edge, but it's not a positive clock edge. So it has to wait for this one. And it remains high until it encounters the next clock edge. When the next positive clock edge, this one, occurs, it again flips its state and returns to the opposite state, the negative state. Again, the negative edge that follows after the positive edge has no effect, but the next positive edge will again cause it to flip. This is Q1. You can see quite clearly that for each full cycle of the input clock, there is just a half cycle of the periodic signal, that is Q1. In short, Q1 has twice the period of the original clock, but otherwise is as likely a signal to itself be called a clock input, a clock signal. It is also a square wave of uniform positive and symmetrical duty cycle, and this now is clearly of half the frequency as the original input clock. What we have done in this figure is to take Q1 and apply it to a second JK flip-flop as its clock input. You can see that from the figure. At the same time, we take care that the second flip-flop also is operating in under flip mode, that is to say, J2 and K2 have also been tied to high, logic high. So, given that this is the input clock signal to a second flip-flop, the second flip-flop should behave in exactly the same way with respect to its own clock, namely Q1, as the first flip-flop behaved with respect to its original clock signal. It should again divide the signal by 2. Of course, there is again the assumption to be made that it was in some certain logical state at t equal to 0, before t equal to 0, and we will again find it convenient to assume that it was in, say, the logical low state at t equal to 0. So now Q2 would be 0 until the first clock edge applied, first positive clock edge applied to Q2. Then it goes high and remains high until it encounters the next clock edge, where it goes down. And again the next clock edge goes up, the next clock edge. So this is Q2. It can be seen quite clearly that Q2 is a square wave whose frequency is again 1/2 of the frequency of the clock signal Q1. So the original clock has now been divided 4 times. Once it has been divided by 2 by the first flip-flop, and the second time it has been divided by 2 by the second flip-flop. Thus Q2 is a clock that is 1/4 the frequency of the original clock. Now let's take a look at the joint readings of Q1, Q2, or rather Q2, Q1. So let's plot Q2, Q1 as a function of time. Q2, Q1. Initially they are both 0 and 0. Then they both become 1 and 1. Then Q2 remains 1, Q1 becomes 0. After that, Q2 goes to 0, Q1 goes to 1. Then they both go to 0 and 0. This completes one cycle of their joint excursion. If you go further, you will see the same sequence repeated once again. 1, 1, 0, 1, 0. For convenience, we shall just translate these digits, these binary digits, into decimal ones and see what we got. We had 0, 3, 2, 1, 0, 3, 2, 1, and so on. Clearly, this configuration is doing a sort of counting. But it is counting backwards, because it starts at 3, goes to 2, then goes to 1, then goes to 0, and then loops back to the maximum value, which is 3, again goes down to 2, goes down to 1, goes down to 0. So this counting is what is called counting down. This is down counting. And down counting, moreover, with a modulo of 4. Down counting modulo 4 means no numbers larger than 3 are recognized, and 4 is identified, 4 and its multiples are identified with 0. That's exactly what has happened over here. This entire circuit is called a ripple down counter. So the way we connected our network has given us a ripple down counter. What is ripple about it? Why do we call it a ripple down counter? There is a certain simplification that we have carried out here in drawing this network, and that simplification lies in assuming that these flip-flop transitions actually occur instantaneously in 0 time. They actually take more time than that, and each time the input makes a transition for each flip-flop, for any flip-flop. The output makes its transition a little later. So let us see what would happen if that were taken into account and we made appropriate changes in the waveforms here. This is the original clock. Let us make corrections for the second signal, that is Q1. So what I will do now is to draw a modified Q1 which lags in time, whose clock transitions lag slightly behind the original clock's transitions. You can see, if you look carefully, that a slight lag has been introduced here. This is just about a third or a fourth of a half clock period. Now let's do the same for Q2 as well with respect to Q1. Again, the slight lag. Of the second flip-flop's response with respect to its inputs. But now if you look at Q2 with respect to the input clock, the delay is considerable. As much as this much. Here again. And again. It is reasonable to expect that if you make a longer chain of JK flip-flops with a larger number of flip-flops with the view to divide the clock repeatedly, then each subsequent clock would be further delayed from the edge transition instance of the original input clock. This can be a very inconvenient matter where circuits with thousands of flip-flops are involved, because the responses of different parts of the circuit would be desynchronized considerably with respect to each other. Hence, the reason to say that these are asynchronous networks, that is asynchronous counters. The reason they are asynchronous is that subsequent to the original application of the master clock over here, subsequent circuits are not any longer correlated with the original master clock, but only with a signal indirectly derived from the original master clock, like Q1 here. So if you had a third flip-flop and its clock input had been Q2, that would be even more remotely associated with the original clock. So there is this gradual progressive loss of synchrony as the number of flip-flops in the chain increases. The solution to this problem is clearly to apply this clock directly to each of the subsequent members of the chain and not use a second-hand derived clock as Q1 is in relation to the second flip-flop. This leads us to a second different kind of counter. But before we even talk about the second kind of counter, which is called a synchronous counter, in which all flip-flops make transitions in perfect synchrony with each other and with the master clock, there is a slight modification of this that is worth discussing, which makes this ripple counter work in a very different manner. That's what we will now proceed to do. What we will do here now is to use Q1 bar as the input to the clock of the second flip-flop rather than Q1 as we have done. So the minor change will consist of taking off this connection and replacing it with this one. So likewise here we will look at Q2 bar. If we did this, let us see what happens. Q1 bar will just be the opposite of Q1, the complement of Q1. So we have Q1 here, let's plot Q1 bar. Then we will take Q2 and plot Q2 bar. So let's do both these right now. Let me first erase Q1 and replace it with Q1 bar. For convenience, I will go back to drawing waveforms which ignore the ripple phenomenon. Here you see is the most strong manifestation of ripple, where all flip-flops, in this case both flip-flops, have got to make a transition or are due to make a transition on an incoming master clock edge. When this happens, there is a rippling, a wave flow of transitions down the chain, with the first one occurring earliest, the second one occurring a little later, and so on. So now I will ignore this phenomenon just to simplify matters and draw the waveforms as I had done earlier. Let me draw Q1 bar first. I had drawn Q1 earlier, so I will just draw Q1 bar as the complement of Q1. Q2 bar similarly would just be the complement of Q2. Right. Now let's look at the sequence of output states Q2 bar, Q1 bar. Initially, both are at 1 and 1. So let me just erase what I had here and write the new values. So they are both 0 and 0. Sorry, they are both 1 and 1 to begin with. And then they both become 0 and 0. So, fine. 0, 0. Then you have 0 and 1. Then you have 1, 0 followed by 1, 1. After this, there is a repeating that begins. After these 4 states, the same sequence starts repeating itself once again, and you get 0, 0, 0, 1, 1, 0, and so on. So let's again translate them into our conventional decimal language, and we get 3, 0, 1, 2, 3, 0, 1, 2, which is clearly upward counting, because you start with 0, 1, 2, then 3, then again start with 0, 1, 2. It is still modulo 4. That is to say that 4 is treated as 0, and the thing repeats its count between 0 and 3, and the only fact is that it started with 1 just because of the choice of initial instant. Otherwise it could well have started with zeros. So clearly this is a synchronous up counter. So this makes it an asynchronous up counter. What we had now was counting down. So now we have counting up. But it's still a ripple counter, that is to say it's an asynchronous counter. It's not synchronous because this ripple phenomenon does occur here at certain points, particularly when you have 1 1 and go on to 0 0 once again. Like here, for example, you have 1 1 and the next transition affects both the flip-flops one after the other, and so the ripple effect would be seen to the greatest extent over here, with this doing something like this and this going further and getting even more delayed, so that you would see clear manifestations of a large amount of delay. So the ripple effect would still occur at those same places as you observed in the case of the down counter. This is then the story of the ripple up counter. Asynchronous up counter behaves like this. As I just mentioned earlier, to make synchronous counters, you ought to apply the master clock directly to the clock input of all the flip-flops. This is what we will now do in the next kind of counter circuit. Here now we have the synchronous counter. In a synchronous counter, as I said a little while ago, the main point is to give the master clock directly to the first flip-flop as well as carry it through directly to the clock input of the second flip-flop. This is what we have done. The J and K terminals of the first flip-flop are both tied to 1, and this is identical to what we had done earlier for the case of the asynchronous flip-flop. So as an asynchronous counter. So the first flip-flop in both counters does exactly the same thing. The second flip-flop, on the other hand, is not configured exactly as it was before. Earlier we had tied J2 and K2 both to 1. Instead, what we do now is to tie J2 and K2 both to Q1, as you can see in this drawing over here. So the clock, master clock, comes to both the first and the second flip-flop, and the J2 and K2 are given to Q1. This is the condition under which we will now observe what happens when the master clock is turned on and the output is observed. Right, so here we have Q1. If you look at the previous figures, you will see that Q1 has been drawn exactly as it was drawn before. No change at all. There will, of course, in fact, be a slight ripple delay between the edge of Q1, the rising edge of Q1, and the rising edge of the clock. That delay cannot be avoided even in a synchronous counter. But then, the interesting part occurs when you consider Q2. In the case of Q2, you see, at this point of time, if you look very closely at this edge, you will see one thing. At the instant this positive edge of the clock has occurred, the first flip-flop was still at 0. Q1 is still at 0. So what can we say about the story of Q2 here? Q1 equal to 0 is applied to both these, J2 and K2. And hence, in spite of the master clock being applied to Q2, applied to the second flip-flop, it will not undergo any kind of change because the input states J2 and Q2 are both zeros and not ones. This is in contrast with the asynchronous flip-flop where JK were both tied to 1 for both the first and the second flip-flop. Here, the second flip-flop receives its input from the output of the first one, and it is undeniable that the output of the first flip-flop at the time of the occurrence of this edge is still 0. So J2, K2 are at 0. Though the master clock occurs here, it causes a transition in Q1 but not a transition in Q2. The transition in Q2 has to wait a little longer. It occurs at the next opportunity, which is the next positive edge of the master clock. Here, at this place, the master clock edge has occurred, and Q1 at the time of occurrence of this is still 1. Remember that Q1's transitions occur slightly after the master clock's transitions. So when this edge of the master clock occurs, Q1 is still at 0. When this edge of the master clock occurs, Q1 is still at 1. Again, Q1 is still at 0 when the third edge occurs. Q1 is still at 1 when the fourth edge occurs, and so on. So, coming to Q2. Q2 is now faced at this point with inputs J2, K2 equal to 1 and a master clock edge, and those are the conditions that allow it to transition from 0 to 1, and it does that here. A similar situation is created only here, where again J1, J2 and K2 are given equal to Q1 equal to 1, and there is a master clock edge and it makes a transition. Similarly here, another transition because master clock edge occurs when Q1 is 1. So this is the legitimate waveform for Q2. Now let's see what the sequence of these bits are. Look at Q1 and Q2 and Q1. You have 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, and so on. So 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, which is clearly an up counter. 0, 1, 2, 3, 0, 1. This has given us a synchronous up counter. Not an asynchronous up counter, but a synchronous up counter. Of course, counting is still modulo 4. So we have synchronous up counter. Now, suppose we want to make a synchronous down counter. What is the change required in this circuit? Very simple. Instead of feeding Q1 to J2 and K2, we feed Q1 bar. Let's make that change over here and connect this to these, as I just did. So, in order to understand what the second flip-flop does, we really need to look at Q1 bar. And let's remove this and draw Q1 bar. Just the complement of this waveform. So I want Q1 bar, which is this is Q1 bar. Now with Q1 bar given like this, let's take a look at what Q2 does and subsequently make conclusions about what Q2 bar does. Now Q1 bar is this. What are the conditions for Q2 to make a transition? The input should be 1. So let's just erase Q2 first, the old Q2, and draw a new Q2, then modify it to Q2 bar. So, is there a transition here? There is. In Q2 there is a transition here because Q1 bar is 1. So if we say that Q2 was 1, it goes to 0. The next opportunity is here. The next opportunity is here. And so on. So now this is Q2. So we have Q2 drawn over here. What I have done just now is to also make a replication of the waveform of Q1, which is just the complement of the Q1 bar waveform already drawn over here. So Q1 bar and Q1, as you can see, are exactly complementary to each other. Now let's look at Q2 and Q1. Q2 and Q1 for this new arrangement. Start from here. Q2 and Q1, for example, here are to begin with 1 and 0. Then they are 0 and 1. Then they are 0 and 0. Then they become 1 and 1. And that cycle repeats. You have again 1, 0. 0, 1, 0, 0, and so on, which comes to 2, 1, 0, 3, 2, 1, 0, which is synchronous down counting. This gives you a 2-stage or 2-bit synchronous down counter. This kind of a network. Of course, this can be easily extended to a larger number of bits, which can count to the modulo of higher powers of 2. This also divides the clock. A synchronous counter, just like the ripple counter, also divides the clock. But the good news about synchronous counters versus asynchronous counters is that the edges of the clocks are never delayed by more than 1 flip-flop's delay from the master clock. This is delayed by the same amount with respect to the master clock as this is. Not in the asynchronous counter, this would be having twice the delay of this one. But they both have the same delay now, and it doesn't get worse than 1 delay. So, in this lecture you have seen how to make counters using flip-flops. We first talked about ripple counters, which were not synchronous, where there was an increasing amount of delay with counters of larger number of bits. And then we spoke of the synchronous counters. Both these counters can be configured either to count up or to count down, as we have shown over here. But this kind of counting is the simple kind. The simple kind, that is to say, where counting is always orderly. It goes through the natural sequence of numbers, either forward or backward. We can do more interesting things with synchronous counters. We can propel them to count in an arbitrary periodic sequence. For example, a 2-bit or 2 flip-flop counter can be made to produce a sequence of 0, 1, 2 and 3 in a different order, say 0, 3, 1, 2, 0, 3, 1, 2. Sequences like these can be generated according to our arbitrary choosing, so long as it's periodic every 4 cycles. This can be generated, and it would be interesting to see how these arbitrary sequence generators are made. You could even make it skip some states and not go through all the numbers that it's supposed to pass through. We will discuss this in the next part of the lecture. The more generalized manipulation of counters consists of several kinds of changes you can make with the way the counter behaves. It is already clear that the counter has at most 2 to the power k different states if there are k flip-flops, jk flip-flops put in one behind the other. Both in the synchronous counter and in the asynchronous counter, there are 2 to the power k, a maximum of 2 to the power k different states. Now, what are the things we can do with these states? We can curtail some of the states by having a smaller number of output states so that certain states are missed. Other things we could do is rearrange the sequence of the states so that a different state comes in the beginning and some other state comes in the end and so on. For example, in this case, which is taken out from the previous down counter, synchronous down counter. What can you do here? You can, for example, maybe consider listing out all the odd states first and then listing out the even numbered states, or the other way around. In all these cases, it must be clear what we mean by a cycle. A cycle is a set of 2 to the power k consecutive states, starting in the case of an up counter from 0, 0 and ending with all ones, or in the case of a down counter, starting with all ones and ending with all zeros. So in the case of this down counter, this is the cycle start position and this is the cycle end position. Likewise, the same points have been mapped over here in this diagram. This is the cycle start, at which point both have become ones, then there is 1, 0, then there is 0, 1 and then there is 0, 0. So this is the end of the cycle. So what are the basic, simplest changes we can do with this? One change we can do is the following. We can curtail some of the states either at the beginning of the sequence or at the end of the sequence. Let us consider this down counter to begin with. This down counter is supposed to count all the 4 states 1, 1, 1, 0, 0, 1 and 0, 0. Suppose we say that we don't want the 0, 0 state. In short, we want to go through 1, 1, then 1, 0, then 0, 1 and then directly back to 1, 1 instead of 0, 0. So 0, 0 is skipped. Now skipping 0, 0 does not mean that the duration of the entire cycle is reduced. That cannot be done. What we can do, so if we curtail say the 0, 0 state, then there will only be 3 states of equal interval, of equal duration, and instead of having a period of 2k times the clock period of t, the counter will have 2k minus 1, in this case 2k minus 1 is 3 times the clock period. So that would be a case of curtailment of the last state, 0, 0. Maybe instead we could consider curtailing the first state, and therefore after you have reached the end of the state 0, 0, instead of going on to 1, 1, you could directly move to 1, 0, then to 1, 0, 1 and 0, 0. So one possible set of curtailed states would be this, which is what we just discussed. So this is last state dropped. Or we could curtail, as I just said, the first state and drop the first state. First state drop. Of course, what is called the first state and what is called the last state depends upon whether it's an up counter or a down counter. For a down counter, the first state is all ones and the last state is all zeros. For an up counter, the first state is all zeros and the last state is all ones. Right. So, suppose we want to curtail the last state. That is, we want to move on from 0, 1 directly back to this. All we need to do is the following. Note that in a synchronous counter, the master clock goes to all the flip-flops. So each flip-flop is working on its own effectively. All it needs to do is not follow the natural course of going on to 0, 0 after 0, 1, but instead go to 1, 1, 1 after 0, 1. Clearly, this means that both these flip-flops should do something different from what they were designed to do. In this case, both are going to zeros. Instead, both should go to ones. The way to do it is to see what are the control signals that can make the flip-flop make the desired transition rather than the natural transition. How do we make this flip-flop Q2 go from 0 to 1 directly instead of 0 to 0? We just have to set the flip-flop. To set the flip-flop, we need to make sure that when it is in the 0-1 state, that is the state that I have called as 1, then a signal should go to the Q2 flip-flop that causes K2 to go to 1. And at the same time, if you consider the first flip-flop, which in state 1 is in has a value 1 of Q1, that should make a transition to 1 instead of 0 again. So this also should either maintain its state or go to 1. So let's look at it like this. Let's make a table. We really don't prevent it from going to 0-1. We make it enter 0-1 momentarily for a small fraction of the clock cycle. And then as soon as it does that, we have a logic circuit to detect that 0-0 has arrived. And as soon as 0-0 has arrived, we send appropriate commands to each flip-flop to make it go directly to the desired state and skip the remaining intermediate states that lie on the natural sequence. So for example, here we make a transition from 0-0 to 1-1 unnaturally rather than allowing 0-0 to complete and then jump to 1-1. Okay? So the moment you see 0-0, and you will see 0-0, though for a very brief period, you should force the system to jump to 1-1. It would appear to us that it has completed the 0-1 state and then jumped to 1-1 directly because the duration of the 0-0 state is extremely brief. But it is to be noted that it does come to pass. There is 0-0 for a short period of time. Yet, for the major period of that cycle, it will remain in 1-1 and then move on naturally through the sequence until 0-1 reappears. So let's see how we do it. What we need essentially is what I will call a detector. In a simple manipulation of the counter of the sort that we are concerned with, we really can allow the system to follow the natural sequence of states except where we want the deviation to occur. And hence, what we will do is, we will keep watching the counter's natural sequence of states until that state where the deviation has to begin comes to occur. And as soon as it comes to occur, we will make the deviation artificially by using an external logic circuit. A logic circuit outside the two flip-flops. So here, in this case, simply put, as soon as 0-0 appears, you have to asynchronously jump to 1-1. How do we do it? Very simple. The first step is to detect that 0-0 has occurred. And when 0-0 has occurred, the detector has to give us a 1 as its output. So the detector has to detect what I will call the takeoff state. The state at which you have to take off from the natural course and make the jump. So the input is the takeoff state. And the output should be a 1, logic 1. That is to say, except when the takeoff state appears at the input of the detector should always give a 0. Only when the takeoff state appears, the detector should output 1. So let's see what happens here. We make a NAND gate, we place a NAND gate over here and apply both Q1 and Q2 as inputs to the NAND gate. We know that such a NAND gate would always give a 1 as the output, except when the takeoff state has arrived, which is 0, 0. When both inputs are 0, the AND would yield a 0 and the NAND would yield a 1. So you get a 1 here only at the correct time and zeros at all other times. Now we make use of this 1 to asynchronously manipulate the state of the flip-flop, and that is done using the SD and CD asynchronous reset and set terminals that are present in the original diagram. These operate instantaneously. They have an effect on the output of the flip-flop immediately rather than at the occurrence of the next clock edge. So these are for setting these respective flip-flops, the SD terminals, and CD terminals are for resetting the respective flip-flop. More importantly, these terminals are what are called active high. Active high. That means to say that if we don't want to make an intervention into the behavior of the flip-flops, we should keep SD and CD always at 0. For example, in this case, except when the deviation state or the takeoff state comes to occur, this output is always 0, the NAND gate output is always 0, and zeros indeed are applied to SD1 and SD2, which is what we want. On the other hand, these two have to be forcibly tied to 0. They cannot be just left open or floating. They have to be tied to 0 for this particular circuit that we want to build. Now, as soon as the takeoff state occurs, very momentarily, you get a 1 over here, and that makes both these flip-flops to set. That is, they will make Q2 and Q1 both go to 1. As soon as that happens, the NAND gate output will go to 0 again, and the flip-flop behavior will come back into the control of the JK inputs of the synchronous inputs rather than the asynchronous inputs. So we have just lifted the flip-flop out of the 0, 0 state, lifted it bodily and thrown it into the 1, 1 state without allowing it to complete the duration of the 0, 0 state. Once it is thrown into the 1, 1 state, it remembers nothing and it naturally progresses through the usual sequence of states of 1, 0 and 0, 1, etc. This is how we have made this circuit to skip the 0, 0 state. Skip most of the 0, 0 state, to be precise. Now the next thing we want to try is to detect and skip the 1, 1 state. That is, we want a behavior which goes like this: 0, 0, then directly 1, 0, then 0, 1, 0, 0, again 1, 0, and so on. Now we really can't do this, nor do we try to. What we do is we have a brief 1, 1 over here. We have a brief 1, 1 over here, just like we had in the previous case. And now let's see, if we want this to happen, what we need to do to go about it. As before, we need a detector for the takeoff state. Now what is the takeoff state here? The takeoff state is 1, 1, because after 0, 0, 1, 1 will naturally follow. But then the moment 1, 1 appears at Q1 and Q2, our ears go up and we immediately say we've got to do something about this. So the takeoff state is 1, 1, and the response to 1, 1 appearing there should be a 1 at the output. So the detector that we have used until now was a Nand gate. What we now need is a detector which gives a 1 only when 1 1 appears at the inputs. This is nothing but an OR gate. So that is what we will replace the Nand gate with. This becomes an OR gate for this new exercise. This is it. But then, where does the OR gate output go? This is just the detector. It tells you that the takeoff state has appeared. Now what do you have to do? As soon as the takeoff state appears of 1 1, you have to make Q2 go to 1, you have to make Q1 go to 0. In short, you have to set Q2, you have to reset Q1. That is, you have to reset the first flip-flop, the left side flip-flop, you have to set the second side, the right side flip-flop. Now, to set this flip-flop, all you need to do is take it here. Just what we have already done. This has to be done. But this part, which we did earlier, is no longer relevant. We take this off from here and realize that this flip-flop has to be reset and not set. Hence, the same one, the active low, is brought over here and given to this. And this is kept permanently at 0. This is kept permanently at 0. So now you see what happens. At all times during the natural course of the natural sequence, when no intervention is supposed to be made, all these asynchronous inputs will be fed with zeros. These two will be fed with zeros because they have been hardwired to zeros. These two will be fed to zeros because the OR gate is going to give you a 0. The detector is not going to go active until the takeoff state arrives. As soon as the takeoff state of 1 1 arrives, this OR gate, the detector, gives you a 1, and the 1 has to be fed in the appropriate places. In this case, you are feeding it here and you are feeding it here. Now, it's very easy to generalize from here that all you need for this general system to work is the following. You need a detector to detect the takeoff state. This detector, for a k-length sequence of flip-flops, or not just 2 but maybe k flip-flops, will just be of this sort. It will have k inputs, 1, 2, k. Rather, you will have Q1, Q2, Qk as the inputs, and this circuit, this detector circuit, should give you a 1 for the takeoff state. This is the case irrespective of whether we are dealing with an up counter or a down counter. The same procedure will work in both cases, because this is just the logical mechanism that tells you how to make a deviation from the natural course. The deviation, therefore, begins with detecting the takeoff state. Once the takeoff state has occurred, now you have got a 1 here. Now let's say that you want to jump to a certain arbitrary state. You want to jump to a certain arbitrary state. Let that state, for example, be ak minus 1 a1. Let this be the state you want to follow the takeoff state. all intermediate states are being skipped. It may not be one intermediate state, it might be several intermediate states that are being skipped. What are these values? These are all binary numbers, and they represent the values of the different flip-flops at the next point after the takeoff state has arrived. In this case, for example, AK is A2 and that was 1, and AK minus 1 was A1 and that was 0. So this we will call as the destination state. Right? You enforce the destination state by applying the appropriate asynchronous forcing inputs to the respective flip-flops. So if AK has to be 0, thus for example, let's say for K in 1, 2 to K, if AK equals 0, then the kth flip-flop has to be reset. Reset the kth flip-flop. If AK set the kth flip-flop. And how do you do it? If you want to reset it, you send a signal to CDK, and if you want to set it, you send a signal to SDK. So the detector output is distributed to the respective places CDK and SDK depending upon whether this is 0 or 1. This immediately causes the sequence to jump from the takeoff state to the destination state, skipping all the intermediate states. Once it goes to the destination state, the detector output again goes to 0, and the detector plays no role in the natural course of evolution until the takeoff state appears the next time. So this is a simple version of the manipulation of a synchronous counter's behavior to skip a certain number of states. As I said, our nomenclature says that there is a takeoff state and there is a destination state, and our interest is to follow the natural course of evolution until the takeoff state occurs, and when it occurs, jump to the destination state. Let me diagrammatically say that, let's say we have all these states, and this is the natural sequence. I would put arrows, but you don't need them really. You know what they are. With what I have taught you, you can arbitrarily choose what is to be your takeoff state. See, after all, this system loops back finally to this, because this will be all zeros and this will be all ones. Sorry. This is the all ones state and this is the all zero state. For an up counter, for a down counter it would be the opposite. So when you reach here, the natural course takes you back to this. You could even think of them as arranged in a circle. Now, our manipulation or our tampering with the behavior of this sequence is to determine a certain choice of takeoff state. Let's say this is what I will call the takeoff state. And let me make this the destination state. So what I want is to follow the natural sequence up to here. This, and this happen naturally. This, as well as this also happen naturally. All I want is to take a shortcut from here and land here. This is the deviation. So this requires a detection of the occurrence of the takeoff state using a detector. The detector has to be designed as I told you here, and the detector's role is to produce a 1 exclusively for the takeoff state and never otherwise. And then the intervention consisting of forcing CDKs and SDKs for k equal to 1 to capital K to their respective values depending upon the choice of the destination state, the values of the destination state. So this completes our lecture on how the natural sequence of a synchronous up or down counter can be manipulated to skip a certain number of states.